All right, cool. I remembered. That's 1 point for me. Let's do announcements to start out. There we are. So things that are coming up or I need you to do. First of all, the welcome survey. I've got about 34 of you that have done it. It's not required, but I would really love if you would all fill it out to make sure that I know what challenges you're dealing with, whether you've taken chemistry before, what your pronouns are, and all those things that I need to know, and that Graham needs to know, and that Mike needs to know to be able to take care of you while this term. It looks like most of you took the time to watch the pre-lecture video on dimensional analysis and to take the quiz on Canvas. So thank you for that. That was my little way of helping to push you along to sign up for Chem 101. So thank you for doing that. This is how we can make more time for active activities during classes by pushing a little bit of that lecturing about just definitional stuff into the before class. So we have more time to work together while we are on camera. Okay, so this Thursday, homework 1 is going to be due at 11:59, and there is usually going to be a Thursday night at 6:30 drop-in tutoring session. I need to check with the tutors and make sure they're still on for doing that, but when I checked in last week, they were still planning on holding it. There is a link for that on our Canvas page. It says something like Thursday drop-in tutoring, and that's at 6:30. So you can join them on Zoom if you'd like some help on your homework. Friday at 11:59, your syllabus quiz will be due. That's a 10-question quiz you can do while looking at the syllabus. It is not supposed to be a memorization tool. I'm just trying to bribe you into actually opening the document and looking. Full disclosure. So please look at the syllabus and please complete the syllabus quiz by Friday. And then remember that during the first 2 weeks of the term, we are requiring you to visit our open hours, either mine or Graham's when he's back, or Mike's. I have office hours right after class today if you guys are not busy during the 11:10 hour. Otherwise, I think Mike is available this morning also, and you can always email and set up an appointment if our office hours times don't work for you. Okay, questions on any of those items before we get started? All right, if you still have questions, you can put them in the chat. The TAs will be monitoring the chat today to help answer your questions. If you're confused about something or you missed something, go ahead and post it in the chat and the TAs will help get back to you. All right, first thing we're going to start with is a little activity about the scientific method. I feel like we've all at least learned about it briefly, and me talking about it for 5 minutes feels really boring. So if you would all go to the Canvas page, please, there is a link under Wednesday that is called Day 2 Scientific Method Activity. Go ahead and pull up that shared PowerPoint file. We're going to work on that together in breakout groups. I'll go ahead and share mine too. Here we are. So the way this is going to work is there are some definitions on slide 2, and there are breakout group lists. So go ahead and find your name, find your breakout group. You're going to be self-sorting today because I'd like you to work with the same people as last time, but I do not have enough hands to sort 40 of you into rooms. So make a mental note, find your room. So what you're going to do is you're going to find the slide with your breakout group's number on it. You are going to find a flowchart for the scientific method with some terms missing. And the missing terms are found in the red box at the side. These guys over here, these are your missing terms. You and your group are going to discuss where these terms need to go. You're going to drag and drop them somewhere into the boxes in the flowchart, into what you agree is the correct spot. Pay attention to the yes and no labels on the flowchart arrow. And please make sure you work together. If I wanted all of you to do it on your own, I would have made 40 copies, but I have only made 12 copies. So I'd really like you to talk to each other as you do this. When you are done, you can come to slide 3 with the blue boxes, and someone can write finished for your group in your group's box. Okay, questions? Clear? There are also instructions in the slides, so you can read those. I'm going to give you 5 minutes. So this is going to be We're going to be moving, but I know you guys can do this quickly. So you are going to assign yourself. So put yourself in the room you were assigned. I will see you in 5 minutes. If you do not have the capability to do that, unmute and let me know, and Mike and I will help sort you. You guys are fast. I didn't even quite have time to assign the TAs a room and y'all were finished already. So excellent work. Let's have a look at what you did here. So it looks like most people form a hypothesis after making an observation, which is right. After you observe something, you make a hypothesis about why you think it might have happened. Then you test your hypothesis by purposely setting up a situation where that observation might happen again, or waiting around to see if it'll happen again. And then if experimental evidence supports it, becomes a scientific theory. And if evidence doesn't support it, it becomes an incorrect hypothesis, and we head back to the top. Cool. So we have all seen this probably in high school chem before. This is the main tool that we use when we are discovering things as chemists. And so today we're going to take our first look down on the microscopic scale and look at sort of like the journey through time of how the atom and its subatomic parts was discovered. So check it out. Here's our schedule. Here we are on Wednesday. Here are some outcomes that we're going to be learning about today. So at the end of today's lecture, you should be able to define a hypothesis as a plausible explanation and a scientific theory as a confirmed explanation supported by evidence and repetition. And you should be able to understand how a scientific theory is modified to incorporate new irrefutable evidence. That's what you just did with your activity. And then in the next bit, we're going to learn how to define an atom as the smallest unit of an element. A molecule is the smallest unit of a compound. We're going to recognize whether a proposed atom or reaction violates a facet of Dalton's theory, learn about the 3 subatomic particles, and illustrate an atom as a very tiny, very dense, charged nucleus in mostly empty space. So this is sort of a visual aid. In this class, we are going to talk about sort of macroscopic scale about compounds and microscopic scale as atoms. And in between, we'll talk about compounds with more than one atom called molecules. So we're going to start all the way down with the smallest size particle. So you may not have seen this lecture style before. This lecture style is where I'm going to write along with you. Pretend this is my chalkboard. So go ahead and pull up your notes. I'm going to do a little bit of lecturing for about 15 minutes, and then we'll do an activity together after that. So everybody can see the notes. We're good and ready. Okay. All right, so we are going to take the time machine through time. You can pick your favorite one, Back to the Future, time traveling car, or you can pick your TARDIS from Doctor Who, or you can pick your Harry Potter and your Time Turner, whatever makes the story more interesting to you. We are going to be stopping through time to look at the development of the atom, what the philosophers thought the atom looked like as we learned about each of the new kinds of subatomic particles. So here we go. Scientists like us use the scientific method, which we just proved that we all know about, to make and test hypotheses about how the world works. So even when we didn't have microscopes and we didn't have very, very special advanced level chemicals and instruments, we still had the scientific method. We could still observe things and make hypotheses about what was going on. And so way back, thousands of years ago, we didn't know a lot about chemistry yet, but we wanted to. The question on everyone's minds was, what is matter made of? we talked about on Monday with Graham, we had a vote about, is this matter or isn't this matter? Matter is anything that has mass and takes up space. But we need to know more about that. We need to know what happens, what is the smallest unit of matter? And so the first person to take a stab at that was way back in 5th century. There were a group of Greek philosophers, and with absolutely no evidence to back them up, they made a hypothesis. They said, we think that all matter is composed of small indivisible particles. That if you divide a material into smaller and smaller and smaller bits, you're eventually going to reach a bit that's so small that you can't break it any farther. And so they called those atoms, which comes from a Greek word for indivisible. And when they made this hypothesis, this was a total guess. They didn't actually have any evidence that this was true. They were just sitting around having thought experiments, and this was what they felt was the most reasonable explanation for what they observed. So fast forward, move our time machine forward to 1789 with Lavoisier. He had a little bit more evidence at his disposal. He could be considered an early scientist or maybe an alchemist. And he made a series of observations about reactions that took place in closed containers. And he learned a little bit more about what happens during a chemical reaction. And so he observed that if you do a reaction inside of a closed container, the total mass of all of the components before and after the reaction remains the same. So if you were to put a candle inside of a glass jar and seal it and burn it until all the candle is melted, the total mass of the container would be the same. All of the mass would be in the candle or in the carbon dioxide released into the air. And there's a fancy name for this. We call this the law of conservation of mass. All of the mass that is there before a reaction is also there after reaction. It is just in a different form. It's transformed into a different compound or a different physical state, or it might look different, but all of the mass is there. And if we know that the mass is the same before and after, then we can conclude that the number of atoms is the same before and after as well, because matter is made of atoms. The number of atoms of each element is also a constant. Let's draw a picture. Notes are boring without pictures, right? So if we have some compound, we can say that compound is made up of red atoms. We have some other compound that's made out of blue atoms. We can react those together, just like Lavoisier did, and we don't necessarily know what will happen. Something might happen or something might not happen. That's very often what chemistry looks like, is reactions not happening. But whatever happens in this reaction, we know that the number of red circles and the number of blue circles is going to be the same on the left side and on the right side, because of the law of conservation of mass. The number of atoms of each element on the left and on the right did not change. So we're moving through time. We know a little bit. We still don't know a lot, but in 1797, we gained some more experimental information from a scientist named Proust, and he gave us the law of constant composition. And what Proust said was the ratio of the masses of each of the elements in the compound is going to remain a constant. So we call this the law of constant composition, or sometimes it's called the law of definite proportions, because the proportion is a constant. And so if we think of an example of a situation like this, where the ratio of the mass of the elements remains the same, we can use a compound that we've all seen before, which is water. And water has the formula H2O. So it looks a little bit like this, a little bit like a Mickey Mouse ear. So there are two elements in water. There's the oxygen and there's the hydrogen. And the ratio of the masses of these two is always going to be the same no matter how much water I have. So maybe I have 16 grams of oxygen and then I'll have 2 grams of hydrogen. So the ratio here is 16 to 2 is 8 to 1 oxygen to hydrogen. So if I had a little bit more water, if I had 32 grams of oxygen, I would have 4 grams of hydrogen. Or if I had 8 grams of oxygen, a little bit less, I would have 1 gram of hydrogen. So the law of constant composition says no matter how much of the compound you have, the ratio of the element masses is always going to remain a constant. All right, everybody still with me? Everybody write in the chat what your favorite time travel vehicle is. Is it the DeLorean? Is it the TARDIS? Is it the time turner? I'm trying to think of what else you can use to travel through time. Magic in general. Anybody? Don't leave me hanging, guys. Come on.
The DeLorean from Back to the Future.
The DeLorean. I do like that movie a lot. Hot tub time machine. Okay. Time stone. The time toad. I don't think I'm familiar with the time toad. I see some other Harry Potter fans in the audience with my own people here. Excellent. Okay, so moving forward in our insert your time machine here, we are going to move on to 1807, and I think I need to move the screen down, don't I? Yes. Okay, in 1807, we meet Dalton, and Dalton is a school teacher, and he doesn't actually do any science. He just teaches what other people do, but he's an excellent academic. He's very well read. He's read all of the literature, and from what he's read in lots and lots of different literature papers in lots of different languages, he sort of condenses what a lot of people's experiments have said into a 5-facet atomic theory. And this is considered mostly correct. Most of what he theorized in 1807, 200 years ago, is still considered correct. So a pat on the back for him. Excellent work. So first facet of his theory, matter is composed of tiny particles called atoms. So he read the works of the Greek philosophers and decided that was still true. So if you take some material and you cut it into smaller and smaller and smaller pieces, the smallest piece that you can reach that is still considered that element or that compound is an atom. Okay, second facet. Atoms of each element are different from each other. Each element consists of one unique type of atom, each of which has a unique mass. So he said if I have a red atom and I have a blue atom, if they weigh a different amount, if they have different masses, they are going to be a different element. Now, this theory was not totally correct. Parts of this are incorrect. This part is correct. Each element has one unique type of atom. The one about the mass, not quite correct. We'll talk about that more in a minute. But he said if you had, let's say this is an element of carbon, and you had an atom of hydrogen. What other color pens do I have here? If I had an atom of silicon, every element is going to have a different kind of atom with a different kind of mass. Hope you came prepared with many colors of pens. That's what you'll need to keep up with this. All right, facet 3. Atoms of different elements have different chemical properties. That's how we can tell atoms apart. We can say, oh, well, does this atom react with water? Does it react with sodium? Does it melt at a certain temperature? Does it freeze at a certain temperature? Those are the ways we can distinguish one element from another. chemical properties of atoms of one element are different from all others. So I forgot what element I said this was. I think I said it was hydrogen. If I had two atoms of hydrogen, then they should have all of the same properties. They should all react with oxygen. They should all store energy. They should all be small and lightweight. All right, fast. Number 4, compounds. So a compound consists of more than one atom. Can't talk and write at the same time. Compound consists of atoms of 2 or more elements combined in a small whole number ratio. So that means we shouldn't be seeing compounds that have subscripts of 2.7 or 3.5 or 5/9. All of the subscripts in a chemical formula should be integers. They should be whole numbers. And the ratio of one number to another is going to be a constant for a particular compound. This is a pretty impressive conclusion from the level of data that they had back in 1807. So we're going to say something like water. Water is a compound because it has not 1, not 2, but 3 atoms in it. It has 2 different elements. So each of these letters is going to represent an atom. The entire thing is going to be a molecule, and the hydrogen to oxygen ratio in this compound is 2 to 1. So we have a small whole number ratio of hydrogen to oxygen, and that ratio is going to be a constant. So if I change the ratio, if I changed it to H2O2, where the ratio is now 1 to 1, this is no longer water, according to Dalton's theory. This is called hydrogen peroxide. This is a toxic liquid. You do not want to drink this. It will not hydrate you. Thumbs down. So when we change the elemental ratio, we change the compound, and the ratio is always going to be a ratio of small whole numbers. Okay, last facet. Everyone's favorite. Atoms cannot be created or destroyed during a chemical reaction. Or rather, they are not. That is not how chemical reactions work. We are not magically creating atoms of oxygen. What we're doing is we're rearranging the atoms that we had in the reactants to make new products. So they are rearranged to give new compounds with new properties. So that means if I gave you a magical, mystical compound that had 3 red circles, and I gave you another one with a purple triangle, and I said, what is produced by this reaction? You probably don't know, because I've totally made this up off the top of my head, but you would know that whatever we made, there would only be 1 purple triangle and 3 red circles. No more and no less on the right side, because that number has to remain the same. Pretty good for a school teacher, if I do say so myself. Right. Thumbs up if you're finished writing. Don't want to yank it away from anyone if they're still going. People with your screens off, that includes you. Good. Okay, emojis. I love it. Not as much of seeing your faces, of course, but we'll take it. All right. You have just learned the first several thousand years of the history of chemistry, more to come. But before we continue, we are going to do some group work. So I'm going to ask you to return to your breakout room for, what time is it now? 10:25, for about 10 minutes. And you are going to start your homework. So I'm going to give you some time to start the homework that's due on Thursday. So the first 2 questions of the homework are about Dalton's laws. So please complete those. And when you have finished those, we'll come back together. If you're super fast, you can finish the first 5 questions because those are about the other features we talked about.
This meeting is being recorded.
Wow, that was so loud from someone's end. Okay, so we have talked about the earliest, and now we're going to fast forward through the next 200 years during which a lot of changes happened because we had a lot more chemical tools, we had a lot more microscopes and experimental measuring systems, and we had more significant figures, which was awesome, Mike's favorite thing. Let's see what we have here. All right, so we're going to continue our timeline. And you can see that I've pre-written my dates. I'm going to attempt to squish 1, 2, 3, 4, 5, 6 pictures on the same page. So recommend y'all start a new page. You'll need the space. Okay, so here's where we stopped. We were at Dalton. Dalton, the school teacher who said, I'm well read. I've read lots of things about atoms and I have a pretty good idea of how they work. So Dalton's picture of the atom was basically just like a big circle. He didn't know what was inside. He just said the smallest unit of an element is called an atom. And he said, if you have 2 atoms with the same mass, we'll talk about this in a minute. AMU is the atomic mass unit. This is one way of measuring the mass of very, very small things. So if I had 2 atoms with the same mass, Dalton would have said these are the same elements. Because every element has atoms that are different, and those atoms are all the same. And Dalton would have said, if I have 2 atoms and they have different masses, one of them at 3 and one of them at 4, not real numbers, just examples, then these would be different. Because Dalton believed that the mass was a way of distinguishing between atoms of different elements. So things really picked up from this point. There are several famous experiments that led to the discovery of things inside of the atom. Thomson discovered that atoms are not, in fact, indivisible. They are the smallest unit of a particular element, but there are things inside, and those things have charges. So J.J. Thomson's famous experiment was rigging up a cathode ray tube, the things that powered those like old-timey televisions that were giant, not like our flat screens today. And it was a ray of particles, and those particles could be deflected with a magnet, and those particles were negatively charged. So with the discovery of negatively charged things, we have to change our model. Now our model of the atom has things inside of it. It has some negatively charged things. And the atom overall has a neutral charge. So even though it has negatively charged things, we know the rest of it must be positively charged so that the overall atom can be neutral. So electrons, those are negatively charged subatomic particles because they are smaller than an atom. They are within an atom. And Thomson named them electrons because he was using an electric device, the cathode ray tube, and he discovered something inside of it, so he named them something that rhymed with electric, which is an electron. And he said, I don't know what the rest of this stuff is inside of the atom, but I know it's got to be positively charged because the entire atom is neutral. It has no charge. And so if you can sort of picture what this looks like, you have a big blob of something with little pieces of things mixed in. So Thomson named his model after a dessert that he liked because he was British and he liked to eat plum pudding, which I understand to be some sort of a yummy dessert that has actual entire plums stuck into it. I don't know about you, but I've never had plum pudding and it sounds kind of gross. So I think we should rename this model. So put something in the chat for me. What's a sort of food that you like to eat that we could rename this after? Some sort of a like big mixture that has small objects mixed into it. See how creative you can be. Tapioca pudding, also not my favorite, but okay, cookie dough, that's a good suggestion. A parfait, oh, the parfait model, I kind of like that one. Oatmeal chocolate chip cookie, schoolyard potion. Is that like mixing milk with soup with pizza and seeing what happens on your tray? Ugh, gross. Green bean casserole, gumbo, oh, yum. Yeah, I was gonna name mine the chocolate chip cookie dough model because it's kind of like the dough with the little chocolate chips mixed in. So it's important to make this a little bit more relatable. So the plum pudding model or the tapioca model or the chocolate chip cookie dough model or whatever you want to call it. That's what the current view of the atom looked like in 1897. Okay, moving the time machine forward 100 years. We have an experiment by Millikan. Again, learning more information about the electron. So Thomson discovered that there were negatively charged electrons, but he didn't know much about them. He didn't know what the charge was, how much negative charge each one of them had, and he didn't know how much they weighed because they're very, very, very light. And so they're difficult to weigh. You can't just put it on a scale. It's not that easy. So Millikan did his famous oil drop experiment. And in the oil drop experiment, he used essentially like a perfume bottle to make a mist of tiny, tiny droplets. And he used a magnetic field to find out how much force was required to move each of those electrons. And he was able to figure out how much charge was inside of each of them. And so Millikan's model looked kind of like Saturn. That's what this is supposed to be, a ring around the outside. We call this the planetary model, because Millikan thought that the electrons were not actually on the inside, like a chocolate chip and a chocolate chip cookie dough. He thought they were rotating around the outside, like the rings of Saturn. So we can draw some electrons here on the racetrack. And then we still think there has to be a positively charged center. We don't know anything about it, but we know that if there's a negative charge, there has to be a positive charge. And Millikan also discovered the mass of the electron, and the mass of the electron is very, very, very light. So we have some positive charged stuff in the middle. We don't know a lot about it, but we know that most of the mass of the atom is there because it isn't in the mass of the electrons, because those are super light. Now things are starting to happen quickly. The experiments are coming. The results are being published in English and more people know English, and so the news is passing faster. We still don't have the internet, but we have this thing called paper, and people mailed it to each other and they sent each other their favorite articles and they said, have you read Millikan's paper? It was about oil drops, big deal stuff. So the next important publication was from Rutherford. And Rutherford's famous experiment was about shooting alpha particles, which were positively charged at atoms of gold. And he tried to figure out what would happen if I shoot basically bullets at this item. Will the bullets go through it or will the bullets bounce off? To try and figure out what was in the inside, because the alpha particles he was shooting at this atom were positively charged. And he said, I know there's positive somewhere inside of the atom, but I'm not quite sure where. And so what he saw was he would shoot these alpha particles and 99% of them would move through as if they hadn't hit anything, just as if they were moving through empty space. But every 100 or 1,000 or so, one positively charged alpha particle would bounce. And what that told him was that there were small positively charged things in the very center. It was not a large positively charged blob after all. there were in fact small positively charged things, but they were in a very small volume at the center. And so to rhyme with the word electron, he named these things protons, because pro means positive. These are going to be positively charged subatomic particles. And there's a famous quote by Rutherford. It was something along the lines of, it was if you'd shot a shell at a piece of tissue paper and it bounced back. It was just absolutely wild and very unexpected. And then here in the part right at the center, we have the nucleus. Nucleus is where those positively charged things live, and it's where 99% of the mass of the atom is contained. We still have those electrons floating around somewhere near the outside. And now that we know that the protons are in such a small area at the center, we know that the atom is 99.9% empty space. There are very, very tiny, very, very light electrons rotating somewhere, more on that later, and very, very small, very, very heavy protons in the center. So for a while, we thought we knew it all that there was to know, until a 1921 paper was published by Soddy about isotopes. And in this paper, he directly contradicted what Dalton had said back here where you can't see at the top of the page in 1807. He said when Dalton made the claim that elements and atoms with different masses are different elements, thought that was wrong. And here's why. Here's what Dalton said. He said, if these atoms have the same mass, they're the same element. If they have different masses, they're different elements. But in Soddy's experiment, he took atoms that have different masses and he looked at their properties. And he said, even though they have different masses, there's the same amount of positive charge in the nucleus of each of these, and they have the same chemical properties. They react with the same things. They bond with the same things in the same ratio. They have the same melting and boiling point. So I think, even though they have different masses, I think they are the same element because they have the same amount of positive charge. Same number of protons, even though the mass is different. And so with that, the definition of what an atom was changed. Instead of the definition of an atom being an atom with a particular mass belonging to a particular element, the definition changed to be an atom belongs to a particular element if it has a particular number of protons. The protons, the number of protons in the nucleus is what defines a particular element. That's the most important part of the atom's little box on the periodic table, is the number of protons that it has. We have one more stop on the time machine, and that is by Chadwick, because someone has to explain what the heck is going on here. If there are the same number of protons and positive charge in the nucleus, but they don't have the same mass, where the heck is that extra mass coming from? What exactly is in here that's making this one on the right weigh more than this one on the left? Whatever it is, it can't have any positive charge and it can't have any negative charge, or we'd have a charged particle. So that subatomic particle must be neutral. So Chadwick named it the neutron. We'll add one final model to our page of art here. So we have protons in the nucleus. We have now neutrons, which are going to be these empty circles. We have electrons, rotating, spinning. We're not quite sure what they're doing, but they're there somewhere in the atom. And the protons and the neutrons are inside of the nucleus. The neutron is an uncharged subatomic particle with a mass around the same as a proton. So we learned all these things before even Mike was born. We were all born into a world where we knew all about subatomic particles, neutrons. We had done experiments with gold foil, living our best life. Okay. Everybody have those pictures ready to move on? Please confirm that you are alive, awake, alert, and finished writing this page. Thank you. All right. So, final page, let's talk a little bit more about those subatomic particles that generations of scientists have labored to learn about. We're going to make a table of those subatomic particles. We are going to talk about electrons, protons, and neutrons in the order they were discovered. Side note, do you need to know the names of all these people and the dates that all these things happened? No, you do not need to know those. It's part of story time. It's part of appreciating how science has changed and developed until you reached the chemistry classroom. Understand and appreciate the story. It would be nice to have an idea of the order of the discovery of the different particles, but you do not need to know anything about specifics. Okay, starting with the electron. The electron is sometimes represented by just an E lowercase or an E with a superscript negative sign to represent its charge. After Millikan's experiment to discover exactly how many coulombs of charge the electron is, we just took that number of coulombs and we just decided we are going to call that 1 unit of charge. And we're going to write the mass of the electron in 2 different units, the gram, because that's sort of like a normal people-sized unit that we're used to, 0.00091 times 10 to the negative 24th grams. And we're going to write it in atomic mass units because that's a more appropriate unit for measuring very, very small things. 0.00055. So even in atomic mass units, an electron is really small. Okay, note, atomic mass unit. Let's write the conversion factor for that. So 6.0022 times 10 to the 23rd atomic mass units are in 1 gram. So an atomic mass unit is very, very small, as are electrons and protons. For our proton, we represent that as a P, or sometimes as a P plus if you work in material science. Proton has a charge of 1 plus, and it is much heavier than an electron. 1.67 times 10 to the negative 24th, or 1 atomic mass unit. And the neutrons' values are very similar. We can represent that with an N. It does not have a charge, hence the name neutral. The mass is not quite exactly the same, but very close. Very close to the mass of a proton. Okay, let's take a second to appreciate how much lighter an electron is than a proton. So here we have the proton, 1.67. And here we have the electron 0.000091. So that's, I'm counting 4 zeros there. That means the electron is 1,000 times lighter than the proton and the neutron. That's like comparing me and my mass to the mass of a skyscraper. There's like 17 little bitty Rachels orbiting around a skyscraper-sized mass in the center of an atom. And so not only is the electron much lighter, but those are also very small in terms of their size. I'm going to draw a big atom. So the size of the nucleus, where 99% of the mass of the entire atom is located, with the protons and the neutrons, is mostly empty space. So the size of the nucleus, on average, is about 10 to the negative 15th meters. And the size of an atom, on average, because there are lots of different sized atoms, is about 10 to the negative 10th. 10 to the negative 10th versus 10 to the negative 15th, that's a difference of 100,000, of 5 orders of magnitude. So the entire atom is 100,000 times larger than the nucleus. If you were looking at an atom, if the atom was somehow large enough that you could look at it, you may not even be able to see the nucleus in the inside because it is so much smaller. Atom is 99.9% empty space. All right, we're going for one more analogy because Appleton. So if we picture the atom as being the size of a football field. I don't know much about football, so this is going to be a terrible drawing. I'm just warning you. I'm pretty sure there are goalposts in a football field, and I think there are some lines. And you're just going to have to imagine the rest of that because that's as good as it's going to get. If the atom was the size of a football stadium, Lambeau Field, the stands, the fans, the yard lines, all that jazz, the nucleus would be the size of a blueberry on the 50-yard line. So if you went to Lambeau Field and you walked in the stands and you walked all the way across the field, you may not even notice that there is a nucleus. That is how small the nucleus is. The atom were as big as a football stadium. Nucleus would be the size of a blueberry. All that to say, atoms are very small, protons, neutrons, and electrons are even smaller, and the atom is mostly empty space, which is an important concept to understand as a chemist, especially when we're drawing pictures that look like this. And we're like, wow, look at how big this proton is. It is huge. That is just because of my limited drawing ability. It is not actually this big. It is very, 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 very small. All right, so that is the end of what we wanted to cover. We have reached the end of the plan. Success. Things you need to know going forward. So remember to go to office hours. Remember to complete the rest of that homework 1. The rest of it is 1 question about the nucleus and 6 questions about dimensional analysis. So go forth and finish that by Thursday night. Your syllabus quiz is due Friday night. And if you haven't done the welcome survey, please do the welcome survey. Mike, any final notes for them? No notes? Cool. Well, you are all free to go.
No notes from me, sorry. It took me forever to get off of mute.
Zoom struggles. All right, you're all released 2 minutes early. Enjoy your Wednesday, and we'll see you on Friday.
All right. Have a good afternoon, everybody.
Thank
Thank
you.
you.
Thank you.